Well, it's about 5:02, and this is my wont. I'm just going to say a few things before the lecture starts at 1 o'clock, really to encourage you to look up into the heavens, because the three things that I think might be worth looking out for in just the next few weeks between now and about Jan the 4th. So the first one, many of you will know about, is the fact that on the 21st of December, perhaps we could have the lights down at the front particularly. Okay, we have a lunar eclipse on the 21st of December. Basically what happens, first of all, the moon starts going into what's called the penumbra of the Earth, where it is partially illuminated. That happens at about 5:30 in the morning. It then goes into the umbra, which is that dark bit in the middle, and I'll tell you when that starts in a minute or two. 5:30, about 6:30 it starts going into the bit where it's really dark. The trouble is, the centre of the eclipse is at 8:16. That's when it's right in the middle of the umbra, and that means, of course, the sun will have risen by then. So we'll only really see the first part of the eclipse here from the United Kingdom. And I've just got a little chart that I did showing the timings here. 5:30 is when it just starts touching what's called the penumbra, and it starts going a little bit dark on one side. 6:32, about an hour later, it starts moving into the umbra. It gets inside the umbra by 7:40, and that's just about when the sun's rising, isn't it? But 8:16 is when it's right in the centre of totality. It leaves that. I mean, anything from here onwards, I'm afraid we're not going to see. But that might just be worth waking up for. If it's nice and clear on the morning of the 21st, the longest day, sorry, the shortest day, longest night. You see, astronomers like long nights, not long days. You have a chance of seeing a nice eclipse. What you tend to see is that the moon starts looking as though bits are missing, and that's when it's going into the umbra here. Then it becomes particularly dark, but when it's near the edge, you still get some light on one side. But hopefully, when it's in the centre, it becomes this lovely, lovely, I suppose, burnished colour. That's the picture that I took of it, of a lunar eclipse a few years ago. Why is it that colour? Well, if you were actually standing on the surface of the moon, looking back at the Earth would obviously be black, the sun would be behind it, but you would see the light coming round through the atmosphere, a sort of a rim of light. Now, of course, when the sun's on the horizon, the red light comes through, not the blue, so that rim would look a sort of a deep red colour, and that's the light that will illuminate the moon. So it looks that lovely deep reddish ochre sort of colour. Now, sometimes it doesn't look that colour, it just looks a very, very dark, dull grey. And that's if you have a lot of dust in the atmosphere that's scattering the light so not much gets through. And that was particularly true in the eclipse following the Mount St. Helens volcano. Do you remember the one that really blew up quite dramatically? Now, of course, we have had a little volcano this year, haven't we? Not that far away. Whether that will affect what we see this time, I don't know. But that's certainly something, if it's clear, when you wake up, or perhaps put the alarm on for 6:30 or something on the 21st, it might be worth having a look. So that's one thing before Christmas. Hands up, how many of you have actually seen the planet Uranus? Hands up. Not a vast number. How many have got binoculars? Right. Before my next lecture, I want you to have seen Uranus. Right? And it's going to be dead easy. The very simple reason, between the 1st and the 3rd of January, Jupiter and Uranus are within half a degree of each other. And Jupiter, has anyone seen it in the sky in the evenings recently? It's beautifully bright. So you can't miss that. It's going to be just a bit to the west of south as it gets dark. Just get your binoculars on Jupiter, put it in the middle, and just a little bit above half a degree, which is about a tenth of a little bit across the field, you'll see possibly a touch of the turquoise colour of Uranus. But even if it just looks like a star, you'll know it's not a star. You will have seen another planet that perhaps you've never seen in your life before. So let me encourage you to do that. And finally, on Jan the 4th, we do in fact have a little meteor shower called the Quadrantids. The good thing this year is that's the day of new moon, so there'll be no moon in the sky. It has a radiant, which is where the meteors tend to come from, which is in the constellation of Bootes, but it used to be a little constellation called the Quadrant, which is basically named after Tycho's mural quadrant that I showed in the last lecture here. He used this to measure the elevation of the stars, and by measuring the time when that happened, he was able to chart their positions in the sky, along with the positions of the planets. So the Quadrantids come from the region of sky that used to be the Quadrant, and it's not far, in fact, from Ursa Major, and basically it's in the northeast. So just look sometime around perhaps midnight, a little bit beyond if you can stay up, and maybe you'll see some of those lovely meteors. If you want to find more about those things and exactly when they're happening, if you can remember the word night sky, if you put that into Google, you'll actually find the web page I write every month to tell you what there is to see in the sky. Some of those little charts there you'll actually find on that page. So night sky tells you what there is to actually have a look in the sky. 1 o'clock. Mysteries of the Universe. I think it's a nice title, isn't it, really? When I was beginning to prepare this, which was about one day after the last lecture, because you don't get much time off doing this job, I thought of a rather famous quotation. It was by Donald Rumsfeld, who was the American Secretary of Defense. And a lot of people thought it was a complete riddle, and perhaps he was learning from his president, George Bush, how to say English. But actually, if you look at it, it contains quite a bit of truth, and it's quite relevant to astronomers. So I've actually slightly rearranged it to make it slightly clearer for us. The first thing he said was, there are no knowns. These are things that we know we know. Now, in fact, this is my 23rd lecture, or 22nd lecture, I think. All of them except perhaps one, when I talked about dark matter and dark energy, I've been telling you what we might regard as the known knowns of astronomy, things that we know we know. That's the easy thing to do, obviously, isn't it? So that's fair enough. But he also says, there are unknown unknowns. These are things that we do not know, we don't know, which you might think is stupid. But in fact, I've been a bit involved in one of the major new European science projects you'll hear about later on. And when you put these forward to your science research councils, you put a science case. You say, what will this telescope do for us? And written in a bit to do with what's called the European Extremely Large Telescope, which we'll come to, it says, on top of this, that's all the things they aim they to do, we are planning for the unexpected, new and unforeseeable questions that will surely arise with the new discoveries made with the E-ELT. Whenever a new instrument has been made with capabilities well beyond those of its predecessors, it's nearly always found something that you weren't expecting. And in fact, one example is going to come up from just a couple of weeks ago, later on. I've been involved with the Square Kilometre Array. I'll tell you what it is later on. But in its science case, the last bit, and I've reduced it a bit, is this. The history of science tells that many of the greatest discoveries happen unexpectedly, perhaps that of neutron stars and pulsars, for example, and reveal objects which are completely different from those that have been envisaged during the planning phase of a new generation telescope. The unique sensitivity of the SKA will certainly reveal new classes of cosmic objects which are totally beyond our present imagination. We are looking forward to such surprises. So we realize that there are unknown unknowns, and we're looking forward to them. But this is what today's talk's about. But there are also known unknowns. That is to say, there are things that we now know we don't know. And these are, in fact, what I've called the mysteries of the universe. There are things about matter that we don't know. What gives matter mass? Why is our universe an antimatter universe? What makes up dark matter? Even worse, what is dark energy? And then there was a period of time, the first 600 million years in the life of the universe, when the universe was dark. How can we learn about what happened then? And then how did the first stars and galaxies form? And how are planets formed in the protoplanetary disks? And finally, is there other life in the universe? Did some of you see the programs that were on last night about this? Yeah, some quite good programs. Okay, so we're going to have a look. I'm going to tell you briefly what these problems are, but the main thrust of today's lecture is really to look to the future of astronomy, show you some of the wonderful instruments that are just coming into play now and hopefully will be coming into use in the next sort of 10 years, the next decade or just a bit beyond. So the first of those questions, what gives matter mass? Well, we all know about fields. This is the field of a bar magnet. I guess everyone at school probably took a bar magnet under a piece of paper and sprinkled iron filings on the top. And you see the shape of the field lines as are shown here. You know the Earth has a magnetic field. How would we know where north was without... Well, actually, we use GPS, don't we? But not to worry about that. But in the old days, we had to use compasses and things. And, of course, when you get current flowing down a cable, like on an electricity grid, then you get, in fact, fields caused to that. Now, essentially, the forces that we observe, the things that make two magnets, two poles of magnet come together, are the result of the exchange, it is said, by physicists, of what are called virtual particles. In the case of the electric and magnetic fields, it's all one, really. They are virtual photons. Notice the word virtual. These particles come into existence for a very brief moment of time, and then they disappear again. In the 60s, Peter Higgs at Edinburgh University and some others came to the conclusion that a few seconds, or in the first second or so after the Big Bang, and I'll be telling you about the Big Bang as much as I possibly know and can in the next lecture after Christmas, there came into effect what has become known as the Higgs field. Now, these things are all very complicated, but at least I can try and give you an analogy. And you have to imagine that this is a post-Oscar party. You know, they have them after the Oscars in America. Now, supposing I somehow managed to get in, I would be completely insignificant. I could even shout probably here, and no one would take the slightest interest in me at all. I could walk through that room, you know, without really being impeded at all. In our analogy, I have very little mass. But then supposing the lady who's won the Best Actress award arrives, possibly having wiped the tears off her face, as some of you remember. And can you see, everyone would want to shake her hands and welcome her and say, well done, and all that sort of thing. She'd be surrounded by a throng of people. Her motion through that party would be incredibly slow. She, in our analogy, has great mass. So the idea is that the Higgs field possibly acts a little bit like treacle, and it slows things down, trying to move through space. That's the idea. All fields have what they call a virtual exchange particle. As I've said, in the case of the electromagnetic field, it's photons. In the weak nuclear forces involved, which cope with, in fact, radioactive decay, it's called the W boson. In the case of the strong nuclear force that keeps the protons and the neutrons together, it's in fact the pi meson. And in the case of the quarks, 3 quarks make up a neutron and a proton, then they're things called gluons. So there are these exchange particles. So if all fields have an exchange particle, so should the Higgs field. And it has, it's called the Higgs boson. And here are some of the particles that make up what's called the standard model of physics. We don't need to worry too much about them, but down here we have the Higgs boson. And just for later, these are the quarks, the up quarks and the down quarks, the first generation quarks. They make up the protons and neutrons, but there are also charm and strange quarks, which are heavier, and then what used to be called top and bottom. But some people don't seem to like the word bottom, so they have actually changed these in a lot of places now to truth and beauty. Which, well, you can have, no, I won't say that. It's not impossible the two could be the same in one case. Anyway, so we're going to talk about the beauty quark later on, but I've always been taught when I was at university it was the bottom quark. Anyway, that's the Higgs boson. That's what we want to know about. How could you make a Higgs boson? How could you tell it was there? Well, the problem is they're pretty heavy, which means you need a lot of energy, E equals mc squared, to get the amount of mass to make one. If during the brief existence that a Higgs boson might have as a virtual particle, if you can give it sufficient energy, it can stop being virtual and it can become real. Doesn't last like that for very long because it will then decay into all sorts of products. But if you have such an event and you surround it with detectors that can detect all of the various products that the Higgs boson might make, then you could perhaps say, we have detected a Higgs boson. And of course, the thing that we hope is going to detect the Higgs boson is the Large Hadron Collider at CERN. It's Europe's accelerator. It's located around the Franco and Swiss border, very close to the Geneva airport. And that's a ring 27 kilometers around. And that's just looking down. There are two beams of particles, protons in general, that go in opposite directions. And at 4 places around the ring, those two beams are made to intersect. And that's where they hope to get collisions. And there are detectors, as we shall see, that look and see what happens. ATLAS is one, CMS is another. These are the first two we'll talk about. But there's also ALICE and what's called LHCb. So there are 4 of these, and they'll all have a role to play in what we're trying to understand. There's the tunnel, and there are 2 pipes down which the protons can also be lead nuclei that travel around. They are kept basically in order by a magnetic field produced by superconducting magnets at a temperature of about 1.9 Kelvin. And in fact, there are 1.9 tons of liquid helium to keep the whole thing cold. And you may remember a year or so, some of the connections between the magnets failed. You got heat cores, and that essentially boiled the helium, and a section of the pipe exploded. That took quite a while to get round. But it's now going okay, as we shall see. The protons travel pretty quickly, 0.9999991 of the speed of light, which is just 3 meters per second less than the speed of light. So they're traveling pretty fast, and that means they have a lot of energy. That's just a view of the grid. There are all sorts of little minor circles that start. You start by accelerating them here, then they get accelerated here, then they get sent round to there, and then one lot is sent that way, another lot is sent that way, and hopefully they will collide and do interesting things. We'll start with ATLAS. And I was lucky enough a few years ago to actually give a lecture in the ATLAS Hall. It's an enormous underground cavern. ATLAS itself, this is a mural of it, but these are sort of human height. This is about 22 meters in height. So these are fantastically big things. They've got lots of magnets and solenoids, and partly to put a magnetic field so that particles with different charges go in different directions. And we'll come back to that idea a bit later on. So this is ATLAS, and it started working earlier this year, and that's looking into it. I mean, this was while it was being built. Quite amazing pieces of technology. And this was on the 30th of March 2010. I think it was the very first detection of anything made by the ATLAS detector. That is when CERN began to operate. This was at 12:58 Central European Standard Time, I guess. So that's the sort of thing that goes on. And these images are made by detecting the tracks of the particles as they go through the detectors. And from all of that, amazingly, you can work out what's going on. The CMS detector is called the compact muon solenoid, and that's on the other side of the circle. And again, it has a vacuum chamber, an enormous detector, calorific things, calorimeters, to measure the amount of energy things have got, and so on. So these are amazing things, and that's sort of what it looks like. And scale size, I think that's a little table down the bottom there. So these are pretty big. And this is what they might hope to see if they detect a Higgs boson. I hope you can all understand exactly what's going on there. I can't claim to, but in principle, their computers will be able to analyze these events and say, oh, we have found a Higgs boson. So the CMS is the thing that is most likely to find one. I'll come back to when it might do that a little bit later on. So that's the first thing. Can we find a Higgs boson to show that there's a Higgs field? If we cannot, physics has got to change. It is a fundamental thing in what we might call the standard model of physics. So if it's not there, in fact, Stephen Hawking says it'd be a jolly sight good if it wasn't there, because things would get much more interesting. Right, but don't hold your breath. The LHC, Large Hadron Collider, will need to run at full power for a couple of years to get an unambiguous detection. In March, I showed you one of the very first ATLAS events. It began to run at about half power. Each of the beams had an energy of 3.5 TeV, that's a lot. So with the impact, it's 7 TeV. Following a winter break, which must be starting about now, it will run at this energy until the end of 2011. That's the end of next year. Then there's going to be a break for 1 year while they do some upgrades before they start running at the full 14 TeV energy range. And that won't begin until 2013. So it's probably only then that they'll have a real chance of detecting the Higgs boson. It's not impossible they could do it next year, but it won't be so easy as when they're running at full power. So, you know, it's going to be an exciting few years. The LHC is just beginning to do some interesting things, which is great. So that's one question. Second question, why do we live in a matter universe? There was a program, again, about mathematics last night. Did anyone see that, with Paul Dirac mentioned? Oh, good, because I can tell you what he said. Anyway, in 1928, Paul Dirac at Cambridge, St John's College, realized that his theory of the electron was a very beautiful theory. He was a great believer in the beauty of maths. To be good, he thought equations produced to try and represent things in the world had to be simple, elegant, and beautiful. And there's a fair bit of sense in that. Anyway, his very, very beautiful equation, actually, one thing it did, it predicted the existence of the spin of the electron, and that, in fact, is very important to us in something we're going to come to a little bit later on. So he realized that you could solve his equation not just for the electron, but also for an anti-electron. We call it the positron, that had positive rather than negative charge. And that would be a particle of what is called antimatter. Well, not long afterwards, in 1932, Carl Anderson, using a Wilson cloud chamber, saw the track of a positively charged, quotes, electron, a positron, so showing that antimatter actually existed. And the thing that worried Paul Dirac was, why was our universe seemingly made up just of matter? He actually thought there might be galaxies out there made of antimatter, or other universes made of antimatter. Now, as you all know, if you combine matter and antimatter together, it is the most efficient way of converting mass to energy, which is how the Starship Enterprise could go at warp speed. So, if you could get some, it would be wonderful. But why is it that our universe is made up of matter? Well, we can make antimatter. Cosmic rays produce quite a lot. That's where the one that was there in that cloud chamber had come from. But if you have a particle accelerator, then you can make it too. And not using the LHC, but another system I've also had a lovely look at, they've recently, it was announced in November, actually made 38 atoms of antihydrogen, which is an antiproton plus a positron, the opposite way around. They trapped them for a total of 6 seconds, 38 little anti-atoms. Not enough to take to the Vatican to try and blow it up, I might say. So we can actually now study antimatter. I've got a movie here, and what is going on here is that they're bringing, from the left, some antiprotons. And the whole idea is you slow them down. They're making them go back and forth in magnetic fields, so they slow down. Because you can only get them to combine if they're going very slowly. And here we have positrons in the green coming in. They're also slowing those down in these magnetic fields until they're barely moving. And then the clever bit is you actually bring them together like that. And here we'll actually see one antihydrogen atom be produced. There it goes. And that will then break up into constituent parts. Well, just a few weeks ago, they managed to trap, I think it was 38, such little anti-hydrogen antiparticles, which is rather nice. So we'll carry on. Now, I'm going to talk about the Big Bang in the latter part of the next lecture. But very briefly, it's this. We believe that initially in the Big Bang, almost equal amounts of matter and antimatter were created. But that there was a very small excess of matter, about 1 part per billion. So for every billion antimatter particles, there were 1,000,000,001 matter particles. Now, as I've said, matter will annihilate with antimatter. So very quickly, all of the antimatter disappeared, and was produced from that a vast number of gamma-ray photons. And they, in fact, gave rise to what's called the cosmic microwave background. And as we've talked about in the past, we now know what that looked like about 400,000 years after the origin. It has the imprint, in fact, of dark matter in it as well. But basically, what we're seeing there, these photons that now permeate the whole of the universe, were the result of the annihilation of all the antimatter with the vast majority of the matter. So all that was left is matter. Now, why should that happen? Well, no one's really quite sure. There seems to be some small asymmetry, 1 part in a billion, between matter and antimatter. And in '67, Andrei Sakharov proposed a number of reasons. One that most people think is likely to be true is called charge parity violation. And they think this is how it controls the way that particles decay. And maybe there's a very slight difference between matter and antimatter. Well, as I've said, we have a thing called the beauty quark, which used to be known as the Boson quark. It's a third generation quark, as I said, with a charge of -1/3 of an E. A little more than about 4 times the mass of a proton. These third generation quarks are pretty heavy, so they're not that easy to make. You need quite a lot of energy. Hence, you need to have the Large Hadron Collider. And there's something called LHCb, one of the 4 impact points around the chain, around the ring, is called the Large Hadron Collider Beauty Experiment. And obviously sounds better than Bottom Experiment, doesn't it? And this is really to explore how matter triumphed over antimatter. There's a cross-section. Basically what happens is you'll get something happening over here, and you'll get a whole stream of particles coming out in this direction. They measure the times at which they travel through the detectors, and they can learn about what goes on. And that is, in fact, one of the first actual impacts shown from a few months ago, and that's a view of it. That's one of the very first interactions that they've had from which they can try and understand what's going on. So by looking at the decay of these beauty quarks, they hope to learn a little bit about why matter and antimatter don't work quite the same way. That again is looking down on it, and you can see all those little lines here. This is telling you what was detected and where. And they have a fantastic computer system to try and work out what's going on. It does actually make the mind boggle a bit. Now, did I not say that sometimes you come across things you don't expect? Well, just a couple of weeks ago, they announced that they detected an unexpected particle, which might be a thing called a tetraquark, something that no one had thought of. So already maybe the LHC is finding unknown unknowns. That's nice. Another nice experiment called ALICE is trying to create the conditions that happened just a billionth of a second after the Big Bang. And you may have heard that in the papers recently, because their first results came out, in fact, since my last lecture to you, I think. What they're doing, in fact, is not actually impacting protons on each other, but lead nuclei, lead ions. And they're 208 times the mass of a proton. And what they say they have just managed to do is, in one of these impacts, create what they call a quark-gluon soup. And that's what we suspect, a pyramidal soup of these elementary particles that existed about a billionth of a second after the Big Bang. So it is true to say that the Large Hadron Collider is trying to teach us about the Big Bang. I think that's pretty good. That's the sort of size. This is an enormous great yolk here, of a magnet. This is heavy engineering, I promise you. And that's the sort of event that they might well expect. But they're more complicated. That's a simulated collision of two lead ions. Look at all the things that come off. And that's a real one. That's one of the very first real impacts of the two lead ions on each other. And another view here. And that was on the 8th of the 11th, so the 8th of November. So just over a month ago. So it's great to say that the Large Hadron Collider is now producing some fantastic science, and I hope it will continue to do so. We're going to have a wait of a year when not much happens, but after that it could be very exciting. Okay, let's move on. What is dark matter? Well, I've talked about that in some detail in one of the lectures earlier on. Just to summarize very briefly, way back in the 1930s, Fritz Zwicky studied clusters of galaxies, in particular the Coma cluster. And he deduced that there must be several times more matter within that cluster than we could actually see. And the simple reason is this. If you took a whole group of galaxies, had them stationary, gravity will make them fall together into a heap. It'll collide, make them the whole lot coalesce into one. That hasn't happened. On the other hand, if they're moving very fast, they'll all fly apart. The fact that that cluster is still there 8 billion years after the origin implies there's just enough kinetic energy in the motion to stop the whole thing collapsing. You can work that out, and it shows the amount of mass that must be there is several times more than the amount of mass that we actually see in the form of the galaxies. So that was the first indication of dark matter. He was a bit of a touchy guy, as you can see from that picture. No one liked him very much, so no one took any attention. That's a pity, really. Anyway, a bit later on, a very nice lady called Vera Rubin, she made observations of a nearby galaxy, and everyone liked her, so everyone took notice. And she observed the rather nearby galaxy is called M33 in Triangulum. You can just see it with your eyes if you know exactly where to look, and it's very dark. Now, notice these lovely red regions here. They're called H2 regions, places where stars are forming. She could observe rotating round the center. Now, you know we can work out the mass of our sun simply from knowing how far we are away from it and how fast we're going around. That's how we've done it. Here, we know how far away this galaxy is. We know that angle. We can measure that distance. We work out how far that's going, fast it's going. That's from the Doppler shift. And we can work out the mass of the galaxy. And again, it was more than it should be. And there's lots and lots and lots of evidence that dark matter exists. In principle, there are a couple of particles that could make up dark matter. The likely one is a thing called a neutralino, which comes out of a physics theory called supersymmetry. That's one. And it's possible that the LHC, using the ATLAS and CMS detectors, may well be able to create dark matter particles. So that would be quite exciting too. So they may give us a clue as to what the particles that make up dark matter are. Now, we can study dark matter in a couple of ways. One way is by what is called strong gravitational lensing. And what happens when a foreground galaxy is in line with a distant galaxy or quasar. That's a very bright galaxy a long way away. And it actually causes more than one image. And the first such serendipitous discovery was actually made using our Lovell telescope. It was then called the Mark 1A telescope at Jodrell Bank in November 1972. And they observed in this region of sky a bright radio source. They first thought it was that, but a bit of a clue here, it wasn't that. It was down here, and there were two bluish objects very close together, 6 arc seconds, very close. The fact they were bluish and bright indicated they were quasars. So the first thing you then do is you go to a big optical telescope and you take their spectra. And amazingly, the spectra were essentially identical. We were looking at identical twins. But we don't expect to have identical twins in the universe. So what is going on? Well, what is happening is that a galaxy, which is in the foreground here, is distorting the space-time around it, and so the light from the distant quasar is coming round two different routes and actually giving rise to two images, image A and image B. And you can see this. This is a Hubble image on the lower right-hand side. That's the quasar. The fact there are spikes there indicates a point-like source. That's the quasar. And that actually is the little galaxy that's doing the imaging, and it's there as well. So we know what's sort of happening. The interesting thing, I may have said before, is that can you see the light that comes directly to us, which is that image, the light's coming straight at us pretty well, takes less time than the light that goes down under the galaxy and up again. It's being curved, the light's being curved under the galaxy. So we see that image at a time 417 days earlier in the existence of the life of that object, that quasar. There's a time difference. Time and space get a bit mixed up. You see, supposing we had an incredible optical telescope in our mind, we could look this way and see a couple being married. At the same time, we could look that way 417 days later and see their first baby being born. Now, it might be the other way around these days, but nevertheless, it shows that time and space are getting mixed up. And also, it actually gives us a way of measuring the expansion rate of the universe, which at Jodrell we've got a very good value for. Now, what was very nice to see that just last week, a first announcement was made of the very first result by a new instrument we call E-Merlin. I spent most of my time in the late 70s, early 80s designing, building and commissioning Merlin. And in those days what we did, we actually linked the telescopes by microwave radio links. In fact, I think, can you just see here, there's a little tower with dishes on, and it's probably not visible there. So we used to bring the signals back by microwave links, just like some of the links around the country that have been used for communications. They, of course, have now been largely superseded by fibre optic links. And that's what we've done. Over the last few years, we've spent £4 million, and we now have our own fibre network linking all these telescopes back to Jodrell Bank. And we have an incredibly powerful computing system that combines all that data together, making, I think it's fair to say, E-Merlin the most sensitive radio telescope in the world at the present time. That's quite something. And this was the very first result that we announced last week, and you may have seen, did anyone see that in the papers or anything? It was in the Times, I believe, anyway, on other things as well. But here are the two quasars, Quasar A, Quasar B. That's the little galaxy I've talked about, and this is the shape of the jet. Now the point is this, that jet was almost certainly straight, is straight, but the dark matter surrounding the foreground galaxy is distorting it. So in fact, by analysing what we see, we can work out basically the dark matter distribution around the galaxy. So it's a very good way of learning about these things. Now, they're not very common. To find them, you need to look at an awful lot of the sky. And that's what a telescope, and I'll tell you about very shortly, is going to do. And this is just showing the Hubble image here with our image, our radio image on top. And we'll look at the top one. Here we go. That's it. So for me, as I suppose one of the fathers of Merlin way back in time, it's a wonderful thing to see. We just hope that in the spending review that comes up later this year, or next year really, we'll be able to survive. Keep our fingers crossed. Now, that's strong gravitational lensing. But also there's something called weak gravitational lensing. You don't get double images, but you get distortions. And this is a wonderful example. This is the Abell Cluster 2218, which are all these foreground galaxies here. But you see these lovely arcs and streaks? Those are the distorted images of a distant galaxy cluster. And the sort of idea is this. Here is the foreground cluster here. Here's our radio telescopes, whatever. Here, or optical telescopes. There is a galaxy, just one of a distant cluster, and essentially the light is forming a sort of an arc of little stretched bits. And again, you can actually see, can you see sort of around here? A little bit of almost a complete circle. So we get these multiple distorted images. Now, usually they're really not very easy to see what's going on. You have to look at them in great detail. We can learn the dark matter distribution by looking at them. And that's the dark matter distribution around that Abell cluster. And this is the sort of thing that goes on. The light from the galaxy is coming through this dark matter region, and it gives you a distorted image, just like what's going on here. What might have been a circular-looking galaxy here has become elliptical. If we can study that, then we can learn a lot about the dark matter. And hopefully this will run. This is what you get if, say, the foreground galaxies were moving in front of the background ones. So you get these wonderful distortions, and by analysing those in detail, we can learn about what the dark matter distribution is. So it's a good way of doing that. And we can look back 6 billion years. And actually it looks as though the dark matter is beginning to clump a bit. It used to be more uniform. This is way back. It's breaking up. It's a lot we don't know. Now, a wonderful, wonderful telescope. It's not being built yet. It's not even been funded yet, but it's going to be, I think, next year. It's going to be called the Large Synoptic Survey Telescope. That's an artist's impression at the moment, obviously. It's going to be at Cerro Paschal. Can't say that very well. The future site, you can see it up there. Not far, in fact, from Gemini South, which is one of the telescopes that the UK has helped build. It's going to have an 8-meter diameter primary mirror. But the optics are absolutely fantastic. This is obviously without any of the structure. You have a first mirror, which is this bit, the outer bit here. The light comes down, it gets reflected up to a secondary mirror. That reflects it down to a third mirror here, and then it goes through 3 lenses, through that hole, to where the detector is. Now, why is it so complicated? Well, that's the actual shape of the mirror system and the ray paths. The point is, they want to have this telescope to have an enormous field of view. So simultaneously, it can look at hundreds and thousands of galaxies to learn about this weak lensing, for example. The actual imager has got 3.2 gigapixels. Now, I've got a 10 megapixel camera. I'm trying to stop myself buying one of 20 megapixels. But this is 3.2 gigapixels. And the CCD array is that big. So the moon would actually sit on that. That's the size of the moon. This is an enormous area. For an 8-meter telescope, this is absolutely incredible. That sort of area of sky seen at one time is what we get with a small amateur telescope. To get it with a big telescope is incredible. And just to show you, this is the sort of thing that an amateur telescope might do, and the LSSD, this area of sky, perhaps even more still. This is what the 8-meter telescope does in the VLT, just a tiny bit. So it's going to be a wonderful, wonderful instrument for learning about the universe as it was. They're already simulating what it can do. This is 1 moon's diameter done with another telescope. The LST will go deeper still and basically look way back to near the origin, really, of the galaxies. It'll teach us an awful lot about how the universe evolved. And that is the top-ranking telescope in the Americans' Decadal Review, which came out a few months ago. So that should be funded next year, operation, we hope, by 2020. It will take over 200,000 images per year, every 20 seconds when it's dark. It's going to be quite amazing. I hope someone can tell you all about it in a few years' time, I really do. So, that's dark matter. What about dark energy? We know nothing much about dark matter. We know even less about dark energy. One thing that made us be aware it existed was by looking at distant galaxies. And they appeared to be fainter and further away than one would expect in the standard Big Bang models. And here's a supernova. This is a lovely nearby galaxy. And can you see that that wasn't there? That's a supernova. Discovered by an amateur with an 8-inch telescope, exactly the same as one I've got. So that's impressive that he did that. Now, we see these all the way across the universe. And this is Hubble telescope images. They are very faint, distant galaxies, and these are supernova that have been seen. That's the before and that's the after. Now, these are a very good way of measuring the distances of things. And they have found that things were not what we thought at all. We've seen Hubble plots before, basically a sort of a linear line between distance and velocity of recession. It tells us the universe is expanding. It was always known that on the large scale it would not be linear because the universe hasn't always expanded at the same rate. But what we thought was, if you take out the slope, there'd be a line that looks basically along here. That's the straight line. This is what we expected, a curve coming down this way. But all these points are not down here, they're up here, as though that curve is doing that and not doing that. That implies that instead of the universe slowing down with time in its expansion rate, it's speeding up. And let me just give you this idea, 2 plots to show this. This red line is what we used to think was the case, that as the universe has got bigger, the rate of expansion, can you see, is slowing, going over here. And on this model, the universe would have been about 10 to 11,000 million years old. We now know it's older than that. And what we think now is that the universe began to expand very quickly, but slowed down because gravity was making it slow down. But about 4.5 to 5 billion years ago, this dark energy that seems to be associated with the vacuum of space and may be related to a constant called the cosmological constant in Einstein's equations took over. And as a result, it looks as though the universe is expanding at an ever-increasing rate. And one way to show this is a sort of a tree rings. Now, tree rings tell you age, but also the distance between each ring tells you what the climate was like. This is sort of a tree ring of the universe. At the beginning, the rings are far apart, but can you see they're getting closer together as gravity is slowing down the expansion rate? But about 4 to 5 billion years ago here, it changed. And now the ring's getting further and further apart, as though the dark energy is making the universe expand at an ever faster rate. Well, if we could find many, many more of these particular type of supernovae in the very, very distant galaxies, that would be a great help to try and tie this down. And the Europeans are proposing to build the European Extremely Large Telescope, 42 meters in diameter. They were aiming to build a 100-meter diameter telescope, which was called OWL. That was the Overwhelmingly Large Telescope. But that seemed to be a little bit too much, so they've come back just to the Extremely Large Telescope, and by goodness, it will be large. There's some comparisons. This is the E-ELT. Those are the 4 8-meter telescopes, well, there's one there as well, of the VLT. That's the standard size class of telescope we have today. They're down in Chile, and this is the Brandenburg Gate, I assume, just to give you some idea of scale. So, perhaps they should have the Eiffel Tower in there as well. So there we go. It's a big thing. It's got a lot of steel in it, and you can't make a mirror that big, of course. So what it will have are over 1,000 1.4-meter hexagonal segments, all make up individual parts of the mirror. It's going to be at a site called Cerro Amazones in Chile, not very far from where the VLT is. That's the current European observatory. So it's the top of this little mountain here. You can see they're beginning to work their way up to the top. That's going to be a brilliant site. Basically, it's very high and dry, not much water vapor. You're very high, so you don't get too much attenuation. And the seeing there is very, very good. This is really about the best part of the world to build optical telescopes. And that's a rather nice artist's impression of how it might look. Well, it'll gather 15 times more light than any current telescope, 15 times sharper images than the Hubble Space Telescope. It'll detect many, many of these supernovae and help us directly determine the evolution of the expansion rate of the universe, helping us to understand dark energy. It looked for other things like variations in some of the fundamental constants, they call the fine structure constant, that some people think might be changing with time. If things change with time in the life of the universe, then physics has got to change as well. Well, we hope that final go-ahead for the E-ELT will be in 2011, and the telescope will be operational by the end of the decade. So that's something to look forward to. Now, the cosmological dark ages, the dark time when the universe was dark. As it expanded initially, it was hot and bright, but then it cooled and it became infrared and radio emission you couldn't see. And then it stayed dark until the very first stars were formed. What happened at that time? Well, what we think happened was that hydrogen and helium clumped together, helped in fact by dark matter, to form the concentrations of gas out of which the first stars formed. As you see, gradually the amount of matter, which we see roughly smooth at the beginning, it begins to concentrate into blobs. This is a simulation with 1 billion particles. That's quite good going. Do you see what's happening? This is as the universe gets older and older. And it's in those great concentrations of gas that the galaxies form and the clusters of galaxies. Isn't that lovely? Like a spider's web. So now we think the universe is a bit like a sponge, you see. It's got these holes and things between it. That's absolutely beautiful. So how can we learn about it? Well, remember I said Dirac showed that electrons have got spin. If an electron and a proton change from having their spin in the same sense to the opposite sense, out comes a photon with a wavelength of 21 centimeters and a frequency of 1420 megahertz. That's in the radio part of the spectrum. A friend of mine, Peter Wilkinson, in about 1991, worked out that because that radiation was so weak, to detect it with a radio telescope, you'd need to have an area of about 1 square kilometre. Not 100 metres across, a kilometre across, even bigger than that. You cannot make any individual telescope that big. So the plan in what is called the square kilometre array is to build a giant array of several thousand, in fact currently 15 by 12 metre telescopes. And that's an artist's impression of how it might look. Where would you put such an array? Well, we want to see the southern hemisphere better than the northern hemisphere. The galaxy shows up much better in the southern hemisphere. So you want to be in the southern hemisphere. You want to be away from people. And the two places that are now shortlisted for the location, one is Australia, and the core of it will be over up here, not far from Perth, I suppose, in the deserts. But there'll be outrider telescopes stretching right over into New Zealand, here and here. Or it could be in South Africa. The centre of it here in the Northern Cape, the Karoo, with telescopes spread right out into Madagascar, up here and over here in Kenya and over in Mauritius. So these are the two possibilities. I would hate to be on the committee that has to decide which of those two it's going to be. We will find out hopefully sometime next year, and then we'll hope to get funding for the first phase to be built to come into operation by around 2018-19, and when the whole is built, should be finished, we hope, by 2024. If you go into Wiki and put square kilometre array, you can find the article I've written about it for Wiki, because I've been responsible for some of the outreach for the SKA for a few years. So that will be a major instrument we hope will come into operation. So we're getting to the end. How do stars form? Well, one problem is that in visible light, the stars form in great clouds of dust. You can't see what's going on. But here, in infrared light, you can see through the dust. So we want infrared telescopes. Here's another example, the Eagle Nebula here. This is an eagle, you see, and that's the fish in his talons. And I'm sure you must have seen that lovely Hubble image showing these dust clouds. These are where stars are forming, but you can't see what's going on. If you can see in the infrared, you can begin to home in on what's happening. And here, in what's called the Horsehead Nebula, we can actually see in the infrared a protostar, which is hidden in the dust here. So if we can see in the infrared or in the short wavelength radio, we can begin to learn about the formation of stars and how planetary systems form around them. Well, the James Webb Space Telescope is being built now to take over from the Hubble telescope in about 2014. Its mirror, you can see, is far greater. It will have to be actually assembled out there in space. There are 4 of the little hexagonal panels, 5 of them rather, being tested in a cryogenic laboratory. It's going to go out to a rather wonderful place. It's called L2, the second Lagrangian point. And there's the Sun, here's the Earth, here it is, 1.5 million kilometres. Now, if you're further out, you go around the Sun more slowly. The outer planets travel around more slowly. So typically, anything that was at this distance further out from the Earth would travel around more slowly. But if it's here, exactly on line, can you see this feels the gravity of the Earth as well as the gravity from the Sun? It doesn't know that fact. It thinks the Sun's a bit more massive, so it goes round a bit quicker. And it goes round at just the same speed as the Earth does. Do you get that? It's very simple, really. It's just got the combined gravity of the Earth and the Sun, and that makes it go around at the right rate, so it always stays in the same place. That's wonderful. There's so many satellites going now, I think they'll have to have an anti-avoidance system before long. It's quite amazing. And it's going to have a wonderful view of the early universe. It will hopefully learn teach us how some of the early stars formed. Comparing some of the early galaxies with today's, we can understand their growth and evolution. It will also help us to understand how the heavier elements were built up in the massive stars. We think the stars near the origin of the universe were perhaps 300 times more massive than our own sun. And in the millimetre part of the radio spectrum, it's wonderful. Again, it's just beyond the infrared, the far infrared, and we're currently building, it's about halfway there now, the Atacama Large Millimetre Array. That's obviously an artist's impression. There'll be 64 dishes that you can move around to make it bigger or smaller. That will help as well. That's the actual site. These are, well, they were said to be extinct volcanoes, but they're not anymore. They've changed, they've uprated them. Dormant. So fingers crossed, all right? Anyway, they're pretty impressive. They're very solid because you get winds up there of 100 miles an hour. That is really quite impressive. They've got to withstand that. And that's a view of the test facility where they're building them and testing them. There are 3 of them there on site. Just a few weeks ago, they had 8 of them on site. And that's a rather nice night picture. But let's hopefully show you a nice picture in a second. It will provide unprecedented sensitivity in the millimetre part of the waveband, and it's going to provide an insight into star birth and also looking locally how stars and planetary systems are formed. So it's going to be a great, great instrument. It should start working in the second half of 2011 and be fully operational by the end of 2012. So it's on its way. It cost £1 billion. It's the largest and most expensive ground-based project that we have under construction at the present time. Typically, all these big things cost at least €1 billion or £1 billion or $1 billion, depending. This is a time-lapse overnight of the 3 telescopes. Can you see them? This is the moon, by the way. Can you see the Milky Way coming down here? I like this because it shows the sky more than anything else. That is called the coal sack, a very dark region of dust, which is what the ALMA will look through. And can you see those stars there? That's the Southern Cross. Okay. It gets a bit cloudy now. But that's the whole night. And these are some of the dust clouds towards the centre of the galaxy, which is over here in Sagittarius. It just shows you what the seeing is like in that part of the world. This is 5,100 meters high. You tend to have oxygen. Isn't that beautiful? Yes, I think it is anyway. And it just shows you what's going to be there. Someday I'd love to see it. Anyway, you never know. So we're nearly at the end. So, final thing to say, just for a few minutes. One of the fundamental questions we have, is there other life in the universe? One of the holy grails of astronomy is the discovery of an Earth-sized planet within its star's habitable zone, just like our Earth is, where the temperature isn't too big, not too cold, just like baby bear's porridge. Now, there is a mission that's now in operation. It's been there for about a year now, since May, I think, in 2009, a year or so. It's called Kepler. It's a spacecraft. And what it's doing is looking for planets to come in front of their star, like this. That causes an occultation. It reduces the brightness of the star slightly, which is seen here, and that lets you show that there's a small planet or a planet crossing the actual face of the star. That's the way it works. And there is, in fact, Kepler, seen in test. You get some idea of the size. It's not that big a satellite, actually. And an artist's impression of it in space. It's looking at a region between Cygnus, that's Cygnus the Swan, and here's Lyra the Lyre. Now, that's the plane of the galaxy. This is slightly off the plane, as is our Sun. But also, it's looking along a spiral arm. The stars it's looking at, over 140,000 of them, are at the same distance from the centre of the galaxy as our Sun. Some people suspect that the galaxy has a habitable zone. Not too good too near the centre, not too good too far out. We're obviously just right. So it's looking in the same basic region. So this is the idea. This is a little planet going in front of its star, goes round the back, comes round again. As it comes in front, can you see it's reducing the light slightly? Obviously, these planets have to have their plane of their orbits in line with the Earth, so we don't see all of them. But that's the basic idea. And these are some light curves of the first 5 planets they discovered. One of them is only a few times bigger than the Earth, here. These are more massive ones. And this is the plot. This is basically how far they are away from their star. This is how big. And these basically are fairly big ones, quite close to the star. Those are the easy ones to detect. Our Earth is down here. No one has yet detected a planet like the Earth. But hopefully Kepler will. But it takes time. If we were looking at our Earth coming in front of our Sun, it does it once per year, doesn't it, from a particular location in space. To be sure you've got it, you've got to look for at least 3 transits. That will take at least 2 years. So we're going to have to wait for about 3 years from when Kepler started to start becoming aware of planets like our own Earth at about the right distance from their star. So a couple of years' time, we should get some very exciting results. To date, Kepler's found 700 planetary candidates. They've got to be confirmed. So far, 8 have been confirmed. But that will come as time goes by. We can look with the Webb Space Telescope at the infrared spectrum of a planet. If we find evidence of water vapor, and particularly ozone in the spectra of a planet's atmosphere, we'd be pretty certain there was life. Because you can't have ozone there unless there's free oxygen. And the only way we know of having free oxygen in the atmosphere is to have something that's keeping it there. Because oxygen's very reactive. It doesn't last long if you take away the source. Photosynthesis does it for us. Something may do it for life on another planet. If you looked at Venus, the Earth and Mars, you'd see the Earth has got this complex spectrum with carbon dioxide, okay, but also ozone and water vapor. But Venus and Mars, just CO2. So it could be that if we get any planets that look like the Earth, just in time, the Webb telescope will be up there. It can look at, hopefully, their atmospheres and maybe, just maybe, say, that's somewhere where life could exist. So you can see, here is the water vapor that tells us that the planet is suitable for life, and that's the ozone in our atmosphere that would actually tell someone, if they're looking at us, that there's possibly life here. And very finally, we might just get a signal from ET. I was involved in what was called Project Phoenix. It's the most sensitive search that's ever been undertaken so far, using the giant Arecibo telescope at Puerto Rico and our Lovell telescope at Jodrell Bank. We looked at 820 stars, out to about 200 light years. Obviously, ET did not phone home, otherwise you'd know about it and I'd be famous, neither of which is true. But the point I want to make is this. We've only looked in our own backyard. 200 light years is nothing. Our galaxy is 100,000 light years across. To be able to pick up a signal from across the galaxy, you need a much bigger antenna. And that, of course, is what we might get with the square kilometre array. So essentially, that would be capable of picking up an intelligent signal from across the galaxy, which is why people like Seth Shostak at the SETI Institute say we're probably going to have to wait until at least 2025, when the SKA is operational, to have a real chance of detecting ET. Well, you never just know. So those are some of the mysteries of the universe, and I hope you've seen some of the instruments that we will be having before too long to help us try and understand them. Finally, I wish you all a very happy Christmas and New Year. In end of January, I'll talk about, well, it's going to be called the Violet Universe. I did think of calling it the biggest bangs in the universe, but I thought that wasn't a very good title. But essentially, we're going to look at hypernovae and cosmic ray bursters, and also about the Big Bang. So I hope to see you then. Thank you for coming. Thank you.